Okay, so hello everybody, thanks for being here. So my name is Clémentine Maurice, and I'm currently a postdoc at Graz University of Technology, and I will talk to you about reverse engineering CPUs and what we can do with that. So the point that I want to make is that even if you have safe software infrastructure, it does not mean that you have safe execution. In particular because information leaks because of the underlying hardware. So your software has to run on the hardware, and the hardware leaks some information. And we have side channels, and these side channels depend on the internal state of the hardware. The thing is that modern CPUs are increasingly complex, and there are large parts that are undocumented. So today, what I'm going to talk about is how we can reverse engineer all the things. So I'll start with a bit of motivation, then talk about reverse engineering the last level cache addressing, and also reverse engineering DRAM addressing. So that's the fun part of reverse engineering CPUs for fun and profit. Then there's some step in between, and then we have profit. I will also have a look at this step in between fun and profit. So a bit of motivation to start. So there is this great fact that I really like, is that Intel x86 documentation has more pages than the 6502 has transistors. So the 6502 is an 8-bit microprocessor that's actually quite old. So I'm not going to lie, it was very much too old for me. I looked everything in Wikipedia. So that was used in the Apple II, and some derivative was also used in the Commodore 64 and in some Ataris. So it was in the year 1975, and it had around 3,500 transistors. And today, if we compare to the CPUs that we have now, like the 22-core Intel Xeon Broadwell E5, so this is the one that was released this year, and this one had 7.2 billion transistors. So that's quite a difference. And for comparison, the Intel Software Developers Manual, as of today, has 4,670 pages. The funny thing is there are actually more manuals than just this one. So quite a lot of documentation. So about this talk, so when people think about reverse engineering hardware, sometimes they talk about a transistor or silicon. And this is not what I'm going to talk about, precisely because we have way too many transistors. It's about more how hardware design can become an attack vector, and how we can reverse engineer these parts to create and to build side channels. So I will focus mainly on Intel CPUs, but some parts also apply to ARM CPUs. So since 2012, we have Intel releasing new microarchitecture every year. And we have basically performance improvement that is quite low between each microarchitecture, around 5% improvement in performance. And this comes from very small optimizations. So we have optimization in caches, optimizations in branch predictions, and we have no documentation on this intellectual property. So that might come weird because I've said before that we have this like 4,000 pages of documentation on Intel processors, but that's mainly how to use them and now how they're built internally. The thing is that all these side channels comes from these optimizations. So we would like to have more knowledge about these CPUs to assess what's the harm that we can do with these side channel attacks. So I'll start on reverse engineering the last level cache, and a bit more background before continuing. So today we have typically set associative caches, and what that means is that we have data that is loaded in a specific set. So this is a cache set, and that depends on its address. So in particular, it depends on these bits of the address. Now we have several ways per set, so here we have 4 ways. And we have a cache line that is loaded in a specific way, depending on the replacement policy. Because usually when the CPU wants to load a new cache line, then it has to evict a line that was previously there to make some room. And that is the replacement policy that chooses which line to evict to make room for the new one. So on Intel CPUs, we usually have several cores, and we have a hierarchy of different levels of caches. So typically we have 3 levels of caches. Level 1 and level 2 are private to each core, so that means that core 0 can access its level 1 and its level 2, but not level 1 and level 2 of, for example, core 3. And we have the last level cache that is here. This one is divided in slices, so as many slices as cores, but it's shared across cores. So core 0 can access slice 0 and also 1, 2, and 3. And it's inclusive, and that means that everything that is contained in level 1 and level 2 will also be in this last level cache. So this inclusive property is actually quite nice. So basically, if you have a line that is in level 1 of core 1, so this red line, that means that it will also be in the last level cache. Now, what happens if we have another line in core 0, so this green line? And it also has to be in the last level cache. So what can happen is that it evicts the line that was previously there, the red line. And to guarantee that we have this inclusion property, we have to evict the red line, because now it's in L1, but it's not in the last level cache anymore. So what the CPU does, it automatically evicts the line that was previously there. So what it means that the core can evict lines in the private level 1 of another core, which is a property that is really, that we exploit a lot in cache attacks. So about cache attacks, so we have caches that improve performance. The thing is that SRAM is quite expensive, so we have small caches. Usually you have several gigabytes of DRAM, and the CPU cache is around a few megabytes. So we have basically different timings for memory accesses. Either data is in the cache, we call that a cache hit, and it's quite fast to access. Or data is not cached, so we have to retrieve it from the DRAM. We call that a cache miss, and it's going to be slow. And cache attacks are leveraging this timing difference. So this is the timing that we have for cache hits. You can see that pretty much all the accesses are between, let's say, 50 and 100 cycles. And now for cache misses, they're a bit slower, and you can see that we will never have any cache miss on the CPU below 200 cycles. So this is the kind of histogram that we build when we want to start a cache attack. Then we say we're going to choose a threshold, and every access that is below this threshold, we consider that it's a cache hit. And every access that is after this threshold, we consider that it's a cache miss. So we have different type of cache attacks. So the first one is called flush and reload. The important thing here is that we have some kind of shared memory between the victim and the attacker. So that can be, for example, a shared library. If it's between virtual machines, that can be memory deduplication. So what that means is that shared memory is also shared in the cache. So if a cache line is cached for the victim, it will also be cached for the attacker and vice versa. So the attackers start by flushing this shared cache line. So it's neither in the cache for the attacker, but also not in the cache for the victim. Now, the attacker wants to know if the victim performing some operation, for example, encryption, access this precise cache line. So this is going to happen automatically. The CPU just loads data into the cache when the victim performs, for example, encryption. And now the attacker wants to know whether or not the victim accessed this particular cache line. So the attacker is going to reload the data and time the time it takes. And if it's fast, it means that data was already in the cache, so it means that the victim accessed it. And if it's slow, then it means that it has to be reloaded from the DRAM, so the victim did not access this particular cache line. And this has quite some fine granularity, because a cache line is only 64 bytes. So the attacker can know if the victim accessed some data that is in these 64 bytes. So this is really fine granularity. Now the thing is that with flush and reload, we need some kind of shared memory, and you don't necessarily have that, especially if you are like in a virtualized environment and you don't have some memory deduplication. For example, on Amazon EC2, you do not have any memory deduplication, so you can't perform flush and reload attacks between virtual machines. But we have another type of cache attacks that we call prime and probe. So in this one, the attacker starts by filling one cache set. So here, this cache set. Once again, the attacker lets the victim perform some operation, and the victim again is going to load some data into the cache. So by loading data, this will evict some of the cache line that belong to the attacker. So here it evicted one cache line of the attacker, and here another cache line. Now the attacker wants to know if the victim accessed this particular cache set. So here we do not know which particular cache line was accessed, but we can know if this particular cache set was accessed by the victim. So to know that, the attacker is going to probe data that it previously put into the cache to determine if the set was accessed by the victim. So on this first line, this is a fast access because the data is still in the cache. And on the second line, this is going to be a slow access because this line has been evicted by the victim. So what the attacker now knows is that the victim accessed some data that belongs to this cache set. Okay, so having prime and probe attack is quite nice because we do not have all these restrictions on the environments that we have with flush and reload. But we have quite some issues with that. So we need to be able to evict cache lines without the CFlush instruction and without any shared memory. So we need to access precise addresses that goes to the same cache set, so what we call congruent cache lines. The thing is that the last level cache is physically indexed. So knowing where a cache line is going to be in the cache depends on the physical address. And knowing the physical address is something that requires some privilege. So what we would like to have is to perform these cache attacks without any privilege. So this is another issue. And depending on the replacement policy, you need to access these cache lines in a precise order. So this is the third problem, because the replacement policy is not always known. So I'm going to concentrate on the first problem. And to have that, we need to know we need to reverse engineer the last level cache addressing. So before that, I will talk about hardware performance counters, because this is what we use to perform the reverse engineering task. So hardware performance counters are really great. They answer this question that we all want to know is what's happening in the system. So it's usually used for performance tuning, for example, to find bottlenecks in programs. That has been used in some side channel attacks because it's quite useful to know what's happening in the system, because you usually have no idea what's happening, and then you try to perform some side channel attacks. But if you can have some information from the performance counters, then that can really help the attack. It has also been used for attack detection, because malicious programs do not behave the same way as benign programs, so that can have some influence on some performance counters. And finally, it has been used by us to reverse engineer the microarchitecture. So this is what I'll be talking about. So performance counters. The idea is that you have some units in the CPU that can monitor some specific and predefined events. So you have a few architectural events, for example, the number of last level cache misses, the number of branch misses, and this will be present in all microarchitecture with roughly the same behavior. And then you have a lot of non-architectural events that really depends on the CPU that you have. For example, if it's a Centibridge, that will be different as if it's a Haswell. Also, if it's an Intel Core or an Intel Xeon, you do not have necessarily the same type of events. So how do we access these performance counters? Well, you have in the Intel manuals, they specify which events can be used, how to access them. So you have either using the model-specific registers or using the PCI configuration space. And you actually have thousands of pages of documentation because you have all these different events that depend on the microarchitecture and on the type of CPU. So you really have a lot of documentation on that, and that's additional manuals. Fortunately, you have some tools to access the performance counters. You have Intel vTune, Intel PCM, Perf Event Open, libpfm4, and so on. So the thing about these performance counters and these tools is that the documentation of the tools is good. So you have someone who wrote a web page that is the unofficial Linux perf event web page, which is subtitled because the perf event developers don't seem that excited about writing documentation, which says a lot. And people are really happy about these tools. Here the review of a satisfied customer, which says this kind of usability is absolutely unacceptable. Users should not be expected to type in magic, CPU, and model-specific incantations to get access to useful hardware functionality. So, a great start. Back to caches. So I told you about these different levels in CPU cache. And in particular, you have the last level cache. So this is the last level cache. And you have the slices that I've been telling you about. And you have, so here is a cache set. And you have the bits of the physical address that says in which set the cache line is going to be. Now the thing is that we actually have a hash function that decides in which slice the cache line is going to be, and that depends on pretty much every bit of the physical address. So you have as many slices as a number of cores, and this hash function is not documented by Intel. Another thing is that it's really annoying for cache attacks, but it's actually not a security feature. This function has been designed for performance because you have one pipeline in each slice, and then the idea was to spread the accesses as evenly as possible across all the different slices so that you have good performance and not a bottleneck on some specific slice. So the hash function basically takes the physical address in input, and as output you have the slice. So how is it a problem for us? So if you want to perform a priming probe on a recent processor that has this hash function, then the thing is that it gets impossible to target a set because you don't even know in which slice your access is going to be. And of course, that will mean that they go to different sets, and you want all your access to reach the same cache set. So it gets impossible to perform these priming probe attacks if you don't have this function that is not documented by Intel. So let's reverse engineer this function. The global idea of that is that we're going to find some way to map one address to one slice. Then we're going to repeat that for every address with a 64-byte stride. The 64 here comes with the size of one cache line, because every address that goes into one cache line will, of course, goes to the same slice, because this is the smallest unit that the CPU cache knows. Then we're going to have this whole mapping, and we're going to infer a function out of it. So this first step, how do we map these addresses to slices? So there's these performance counters I've been telling you about. We also actually have different other methods to do that. We can use CLFlush instruction because this one has a different timing depending on the slice the access goes to. And we can also use the memory accesses because in the same way as the CLFlush instruction, this has different timing depending on the slice. So I'll be telling you about the performance counters method. And if you want even more detail than that, you can check our red papers that was published last year. So how do we map physical addresses to slices using the performance counters? So we have different units that can monitor different events, as I've been telling you about. And we have C boxes. So we have one C box per slice. And we have a particular event that is called uncbo cache lookup for uncore C box cache lookup. And this event counts accesses to one slice. So the idea is that we're going to have one address. It goes through the hash function. So here it says it goes to slice 0. And then the uncbo cache lookup event counts +1. Same goes for a second address, goes to slice 2, +1 here, and so on. So what we're going to do is that we're going to translate virtual to physical addresses because the hash function takes into input physical addresses. So for that, we use proc-bit pagemap. This interface is now privileged, but here we assume that we are on our own machine and not on the victim machine. And once we have the function, we can use it on the victim machine without any privilege. So we're going to set up a monitoring session, repeatedly access one address and one address only. Now the thing is that the CLFlush instruction is already counted as an access. So it will be counted by this event in particular. And we're going to read this event for each C-box. Then the slice that is mapped to the address is the one that will have the maximum lookup events. So this is the kind of result that we have. So here we have different addresses, so 4 addresses. And we have the number of events for each C-box. So in green, C-box 0, and so on here. So as you can see, we can clearly map. So this address has really a lot more events for C-box 0 than it has for the other ones. This one for C-box 1, this address for C-box 2 and 3. So here we can clearly map this physical address to this C-box, and so on. So the gory details now. So I've been telling you about all these great tools and how people are really happy and how they are super well documented. So I tried. I did not manage to use a single tool. So I programmed these model-specific registers manually. So this is not great for for a lot of reasons. In particular, you have the same model-specific registers and the same event for all Intel Core CPUs. But the documentation is buried somewhere in the volume 3 that is only around 2,000 pages. And then for Intel Xeon CPUs, then each microarchitecture has its own Uncore performance monitoring manual. And of course, it's not the same model-specific registers, it's not the same events, so it's not nice to program. So this is the kind of documentation that you have from the Intel manual. So here's the layout of the model-specific registers that we use to select the precise event that we want. So basically, we're going to set this bit to enable the counter. For this one, that's it, and set these bits to select the precise event that we want. So this is the kind of documentation that you have. Then you have these lots of pages with lots of tables with every event that you can monitor. So you have to find the right one, which is, yes, this here. So this is great. So Intel provides you the list of steps that you need to perform to monitor what you want to monitor. So first you have to disable the counter, which is essentially writing to some model-specific register, then resetting the counter, select the event to monitor, enable the counting. Then you can call the function that you want to monitor. So here it's basically a loop of CLFlush for one address. And then you can read the counters. So when you do that for every address that you want, you will have some mapping of your addresses and then the slices. Then you need to infer a function out of it. You have 2 cases. Either it's a linear function, which is the case if you have a number of cores that is a power of 2. So if you have 2 cores, 4 cores, 8 cores, and so on. And you also have the case that it's not a power of 2 number of cores. Like if you have 10 cores, then you will have a nonlinear function. So here we'll just be talking about this case because it's really the simplest one. So the function is linear in this case. So it's going to be a XOR of address bits. XOR has nice properties, so it's commutative, it's also associative. So you can treat all the input bits independently. And so for each bit of output, So if you have 2 cores, you will have only 1 bit of output. If you have 4 cores, you will have 2 bits of output. So for each bit of output, basically what I did is finding 2 addresses that differ by a single bit, then comparing this output. If the output is different, then the bit is part of the function. If the output is the same, then the bit is not part of the function. And this is the result. Basically, we have only 3 functions, and they only depend on the number of cores. And that is valid for every architecture that we try. So Sandy Bridge, Ivy Bridge, Haswell, and Broswell. It's also valid for Core and Xeon CPUs. And here you can see that this was the result that we have for 2 cores. And this function is actually the same as this one for 4 core and this one for 8 cores. And then we have O1 for 4 cores, which is the same as O1 for 8 cores. So in the end, we actually only have these 3 functions, and the number of functions that you use depends on the number of cores. So we have our function. What can we do now? So we have our function. So now we can basically perform all the prime and probe cache attacks. We have first covert channels. So the idea here on covert channels is that we will have 2 processes that will communicate with each other, even though they are not allowed to do so. You can think, for example, of 2 processes in 2 different virtual machines. They're really not allowed to communicate, but if you use a covert channel, then you can maybe make them communicating. You have a different type of attack that is side-channel attacks, in which you will have not 2 malicious processes, but only 1. And this one malicious process will spy on other benign processes. You can use that, for example, to steal crypto keys or to spy on keystrokes. So I'll start with covert channels. So the nice thing about prime and probe is that it has low requirements. So it will work, for example, between virtual machines in Amazon EC2. And the main issue that we have with this type of covert channel is that we have a lot of noise due to other programs, because they will all compete for this cache, which is a few megabytes. You also have the issue that the sender and the receiver are not necessarily scheduled at the same time, especially if they are in between 2 different virtual machines. So that gives a lot of errors in the communication in this covert channel. So what we did is using error detection and error correction, and we managed to have an error-free covert channel, even in presence of really extreme noise. And we ran that in native environments. So we managed to have a bitrate around 75 kilobytes per second. And it also still works without any error if you put stress M1 on the machine. So that will use extensively the memory, but it only reduces the bit rates, and we still have no error whatsoever. We also did that on Amazon EC2. So we reserved 1 instance, and we launched some virtual machines on the same physical machine. And we managed to have a communication between 2 different instances that had basically no network communication between them. So in this case, without any noise, we managed to have 45 kilobytes per second. And then we played and tried to see if we could break our covert channel by launching, for example, stress on the center VM or on the receiver VM. We had also a third VM that was co-located. We tried to run web servers, saving files on all 3 VMs, putting stress M4 on the third VM, stress M1 on the sender and receiver. Still it didn't break. We still managed to have some connection. And on the worst case, we still had around 34 kilobytes per second. So then we thought what we can do with this error-free covert channel. And we had an idea is that to basically build an SSH connection over the cache. So we had 2 virtual machines that have no network connection, and they are using the cache to send bits to each other. So basically, we used sockets, and then the covert channel sent the byte to the other virtual machine, which can read them. So that's actually a bit overkill because with an SSH connection, everything will be encrypted and nobody's actually monitoring the cache. But you need to have exactly 0 error or else the SSH connection will break. And that was a good example of how you can maintain really error-free connection using the cache. So now we can also have side channel attacks. So the first time we had these two malicious programs. Now we have only one program that spy on other program. We can build side channel attacks against crypto. For example, you have the one AES implementation that is software only and that uses T-tables, which are pre-computed lookup tables. And unfortunately, this implementation has been known to be vulnerable against side channel attacks since 2006. So the idea is that you have P, your plaintext, and K, your secret key. And the algorithm is going to compute an intermediate state at each round of AES. And on the first round, the access table indices are P, XOR, K. So this is a known plaintext attack. That basically means that if you recover the access table indices, then you will also recover the key because it's just XOR. So I've told you that we can monitor a lot of things with the cache. So the idea is that now we're going to monitor which table entry is accessed. So here you have the addresses that are monitored, and this is basically which table entry we monitor. And here you have the plaintext byte values. So when you have some dark squares, it means that we had a lot of cache hits. So it means that this entry was accessed. So you have this for flush and reload. So for flush and reload, we have absolutely no noise. And you have this for prime and probe. You can see that we have some noise, but in each case, we are able to find which T-table entry was actually accessed. So these images are for a key that is all zeros. But if you can manage to have this nice diagonal, then if the key changes, just the pattern will change. But in every case, you will be able to find which table entry is accessed, and then you are able to recover the key. So this is the kind of attacks that we can do with cache attacks. It's actually quite powerful. So even if we are in conditions like prime and probe where it's not exactly ideal, we have a lot of noise, but we can still have covert communication and perform powerful side channel attacks. So the takeaway on the cache attacks is that basically, even if you remove like the CL first instruction, then you can do this flush and reload, which had no noise and which was nice. You can still perform prime and probe, so it's really not a good countermeasure. Yeah, because we can fall back to prime and probe. And we had this undocumented function that prevented us to perform prime and probe attack, but just reverse engineering it, basically we can build all the side channel attacks again. The other takeaway is don't hesitate to be creative. So performance counters were never meant to reverse engineer CPUs, but you can use that, so you should. Okay. After CPU, I'd like to talk to you about reverse engineering the DRAM addressing. So again, a bit more background before continuing, because that's quite different from the caches. So you've probably all seen this. So this is a DRAM module. You can have several DRAM modules, of course, in your computer. So you will have different channels. Each side of the DIMM is called a rank, and you have different chips on each rank. Now, in one chip, you have different banks, and in one bank, you have different rows. And the bits themselves are cells in these rows. And when you perform one access, what the CPU does, it activates one row, and it copies it to the row buffer. So the thing is that Durham internally is only capable of reading entire rows. You cannot just read one byte from the Durham. It will always read the entire row. And you have capacitors that discharge when you read the bits. So the idea is to buffer the bits when reading them from the cells and write them back when you're done. And this is what the row buffer does. So how reading from DRAM works. So here the CPU wants to access row 1. So this is the row in orange. So row 1 will be activated, then copied to the row buffer, and then returned to the CPU. Now, if the CPU wants to access row 2, it needs to activate row 2, and then it needs to replace what was in the row buffer to be then returned. And this is actually quite slow because we have this row conflict. There was something else in there, and we need to probably write back to whatever value was written on this row, and then copy the new row. Now, if the CPU wants to access row 2 again, what happens is that the row 2 is already in the row buffer. So it can be returned, and this is way faster than the previous case. So you again see the pattern. Probably we have a case that is fast, a case that is slow, and basically the idea is that the row buffer is essentially a cache. So we have these timing differences. Previously we had cache hits and cache misses, and now cache misses can be basically divided into row hits and row conflicts. And here you have one part that is only row hits and no row conflict at all. So this is the kind of timing difference that we're going to use. So row buffer are caches, and we can observe timing differences. So how can we exploit now these timing differences? The idea is that we will need to target addresses that are in the same channel, in the same rank, and in the same bank. And the Durham mapping is, again, undocumented. So let's reverse engineer it. So we had one first phase where we did physical probing and also used the high bandwidth oscilloscope. So that was a PhD student in our group who did that, basically accessing one address and then probing in which, like really physically where it goes in the DRAM. So I believe that was actually a bit painful to then do that like really manually. So we wanted to have an automated approach. So that was our second phase, and this one was software only and fully automated. So we wanted to do that the lazy way, just run some programs, give us the DRAM mapping, and we're done. So the idea is that we're going to use the timing differences that come from the row conflict. So in our approach, we start by selecting a random base address that will go into some bank. So this is really a schematic and high level and really simplified view of the DRAM. So here we have one bank, and we have, so 0 is one row, then we have row 1, row 2, etc. So we start by selecting an address that goes into one bank. And then what we're going to do is measuring the access time when repeatedly accessing the base and this random address. And here, they go into different banks. So that is going to be quite fast because the row buffer never needs to change. So here we have, again, in a different bank, and here we have the case where we have one address that goes into the same bank as our base address. And this is going to be slow because then we have to each time copy the row to the row buffer. And this is way slower than when we had the addresses in two different banks. So again, same bank. Then we do that for with other random base addresses. Goes to different bank, same bank, etc. So then we have for each bank a set of addresses that are mapping to this bank. We have then basically the same thing as we had for the last level cache. We now need to infer a function out of it, so we can either see that as a linear equation system, and the solution will give us the bits that are used for the mapping functions. Then you have the approach 2 that actually works well. You just can brute force all the functions and then verify with the ground truth if it's correct or not. And then you have the right function. It sounds tedious, but it was quite fast, in the order of a few seconds, to find the correct functions. So that gives us a toolkit to reverse engineering the mapping fully automatically. And this is the kind of result that we have, for example, on our Haswell server system. So that gives us 1, 2, 3, 4, 5, 6, 7 functions. And then, yeah, we have our whole set of functions, and we're happy about that. So you actually have the code here on GitHub. If you want to try on your own machines, you're very welcome to try. So again, we have this function. What can we do now? Well, we can do DRAM addressing attacks. The idea is that we are going to infer some behavior from memory addresses similarly to the way we had with cache attacks. The nice thing is that it also works across VMs, it works across cores, and unlike cache attacks, it also works across CPUs, because different CPUs do not share a cache, but they will share the DRAM if it's the same machine. We can build covert channel and side channel attacks basically as with the cache. So how do we build first a covert channel? So the idea is that we will have the sender and the receiver that will agree on one bank. So this bank. We have the receivers that continuously access one row. So here, let's say this one. No, this one, yes. So again, we have the row that is activated, copied to the row buffer. And then we have the first case. So the sender wants to transmit a 1. What the sender does is that it accesses a different row that then is also activated and copied into the cache. And when the receiver then has his next access, then this will be copied in the row buffer. And this is going to be slow. Now, if the sender wants to transmit a 0, well, it simply does nothing. Then the row is the one of the receiver in the row buffer, so it's going to be fast. And we have, again, this difference between fast accesses and slow accesses, and this is how we differentiate between our zeros and our ones. So we evaluated this in native environments, and it's quite fast. We obtained 1.6 megabit per second. We also evaluated between 2 different virtual machines, and we have around 600 kilobit per second. We also implemented that in JavaScript because we thought the not so nice thing about covert channels is that you have to have 2 binaries on the victim's machine. So the idea is that here we will have the sender inside a virtual machine that has like no network accesses, and you think you're safe because you have no network accesses. But if you have a sender inside this virtual machine and the receiver that runs in some web page outside, then you can trick your victim to go see this page, and then the sender and the receiver can communicate through the DRAM, although the virtual machine has no network access. So we focused more on the error-free communication than on the speed. So this one is much slower than the native environment, but we still have 11 bits per second. So if you want to, let's say, extract one secret key or other sensitive information that is quite small, then it's actually practical to use that. So that was for covert channels. Now, similarly to cache attacks, we can also do side channel attacks. So here the setup is a bit different. The spy and the victim are going to share a row. So when I say share a row, it's not shared memory. It's really they will each have different 4 kilobyte pages. But these pages arrive basically in the same row. So we have first the spy that accesses a different row, so copy to the row buffer. Then the spy wants to know if the victim accessed or not this particular row. So in this case, let's say the victim accesses it. It's again copied to the row buffer. And when the spy accesses this same row, then there will be no copy. So this is going to be fast. In the second case, so again, the spy started by accessing its own row. So in the second case, there is no victim access on this row. And when the spy wants to access this row, then it has to be copied to the row buffer, and it's going to be slow. So here the spy knows whether or not the victim accessed this particular row. So this gives us two related questions. First, what's the chance that we can share a row with abundant victim data? Then what kind of spatial accuracy do we get? So the idea is that the smallest unit of physical memory is 1 page, and pages are usually 4 kilobytes. And one Durham row is usually 8 kilobytes. So we need the victim's address and our address in the same row. So we have to think, what can happen? So if you say that you have 2 pages that share 1 row because 1 page is 4 kilobytes and the row is 8 kilobytes, then you're not wrong, but you're also not really right. So why? The idea is that the 4 kilobyte might not be in a single row, and that depending on the function, a page can be distributed over multiple rows. And this is the case in particular if address bits 0 to 11 are used for the mapping. So for example, on Skylake, it uses the low bits for channel and bank group. So in our case, we had 1 physical page that was distributed over 4 different rows. So this is how it looks like. We have our 4 different rows here, and we have a 4 kilobyte page. And the idea is that we have 1 page here, so for example, page 2, that is distributed around over these 4 different rows. And each row has parts of 8 different pages. So you have a mapping that is quite complex that looks like that. So you have this 128 bytes that goes into this row. Then this one goes into the same row, and so on. So the mapping is not exactly trivial. But yeah, the thing to remember is that we can have 1 page distributed over different rows and different pages into 1 single row. So the number of pages per row, that depends on the Durham configuration. So if you have, let's say, 2 DIMMs or 1 DIMM, it's going to be different. And it also depends on the CPU architecture. So this will depend on if it's like a Sandy Bridge, Ivy Bridge, or as well. So for example, on Sandy Bridge with 1 DIMM, you have 2 pages per row. Ivy Bridge with 2 DIMMs, you have 4 pages per row. And Skylake with 2 DIMMs, you will have 8 pages per row. So what can we do with that? Side channels again. So we wanted to spy on keystroke. This is something that we already did with the cache. And the idea is that we're going to, so we need to find each time which particular address do we monitor then that reacts to this keystroke. So we are going to launch a template attack, and that works by allocating a large fraction of memory to have a common row with the victim. And then we're going to profile the memory and record the row hit ratio for each address. And then we will have 1 address or maybe several addresses that will have a high row hit ratio. And then we can monitor, let's say, this particular address that had a high row hit ratio. And so this is what we got when we typed in the URL bar of Firefox. And we could really precisely know when we had 1 particular keystroke. So this is just for annotation. We do not have which particular key was accessed, but we had the timing in between different keystrokes very precisely. So we have the timing granularity in terms of nanoseconds. And especially important, we don't have any noise. As you can see, there is no additional point that we did not type, and also no point missing. So we have quite nice and targeted attack here. So more attacks on DRAM, maybe rowhammer attack. So rowhammer was explained really nicely by Motherboard Vice. So they said it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. I really like this quote. So this works by activating one row and then another row, etc., until you have your bit flips in a row that you absolutely never accessed. So this is quite bad. So the thing is that we have the CPU cache in between the CPU and the DRAM, and that to have these bit flips, you need to access the DRAM, and only non-cached accesses reach the DRAM. And for that, all the original attacks use the CL flush instruction. So the idea is that you flush the line from the cache, and then next time it will be accessed from the DRAM. So each time, basically works like that, better with a figure. So you have one access from the DRAM, it goes into the cache, and then you flush it, it's gone from the cache, and then next access will be served from the DRAM, and so on. Flush and reload, until we have our bit flips. So I just said flush, reload, and just before I talked about flush and reload attacks. So the idea is that the core of rowhammer is essentially a flush and reload loop, and so I think it's widely known as an attack on DRAM, but for us it's also an attack on the cache, because you have to flush it from the cache somehow. And we thought we were going to do rowhammer without the CL flush instruction, because the CL flush is quite dependent on the instruction set architecture, and we want it to be independent of the instruction sets. And for example, you don't have CL flush in JavaScript. So our approach is to use regular memory accesses to evict the lines that we wanted to evict, and this borrows techniques from cache attacks. So we're going to do rowhammer prime and probe style, basically. Again, if you want more document on that, you have our Timva paper. So how does that work? The idea is that we're going to load addresses that have nothing to do with the bit flips, and we're going to fill the cache set until it evicts the data that we were after, and then we can reload the data from the DRAM, and we do that several times until we have our bit flips again. So we have two important requirements for rowhammer. First, it really has to be uncached memory accesses, so it needs to reach the DRAM. It also really needs to be fast, because this is actually a physical problem. The idea is that you want to perform several accesses so that the cells are discharged, and you want to do that before the next row refresh. So if you're too slow, you won't have any bit flip. So basically, you want to optimize both the eviction rate and the timing. There were some of the challenges for rowhammer.js, and I will not have the time to go into details of all the challenges, but some of them where we need to know which addresses to access first in the same DRAM channel, rank, and bank to cause the bit flips, but also in the same cache set to evict the cache lines. And this is solved by reverse engineering both the DRAM and the last level cache addressing. So this was really an attack that necessitated really a lot of preparation before we even had those bit flips. But it works quite well. So here you have the number of bit flips we had within 15 minutes. So first with the CL flush instruction, then is in native environments, so no JavaScript with using the eviction. So you can see that we have less bit flips, but so here each time we change the refresh interval. This is something that you can change into the BIOS, and we did that to evaluate basically if we could have like bit flips with the default configuration, or if we needed to change this configuration. So for CL flush and using the cache eviction, basically we had less bit flips, but we had them, each time you have bit flips with the CL flush, you will be able to have bit flips without the CL flush instruction. And then in JavaScript, we had, again, less bit flips, but also you needed to have a refresh interval that was higher to have some bit flips. So if you have some bit flips in native environment with CL Flush, you may not have bit flips with JavaScript. It really depends on the machine. We also tried Rohammer. So the original article for Rohammer was, it's a problem for DDR3. And then manufacturer were like, but it's okay, just buy new DRAM, the DDR4, it doesn't have any problem, and you're all safe. You just need to buy other DRAM. Great. So we tried before having the reverse engineering of the DRAM addressing, and we indeed had, so nobody could find bit flips for DDR4. Then we used the reverse engineering of the DRAM addressing, and we could find some bit flips on DDR4. So we think it's basically because the accesses are reordered in the memory controller, and then if you're not targeting exactly the same bank, etc., then you won't have any bit flips. But if you have this function, then you're able to target a bit better, and then maybe have some bit flips. So DDR4, still vulnerable to Rohammer attacks. We need to really find something better. So as a conclusion, so some CPU components are undocumented. It makes attack harder, but it's not really, so they did not document that, not for security reasons, but more likely for business reasons, because each component has some optimization that makes the next generation a bit better, and probably they didn't want to give some advantage to concurrence. The thing is that it's actually not that hard to reverse engineer modern CPUs. So I would say, at least at this level, again, we're not looking at silicon level, just the high level, but it's really not that hard. And it's also very crucial to know more about CPUs to assess these side channel risks. And here we have a conflict of interest between business and security, because so manufacturers do not want to have all the documentation of the internals of the CPUs, but also if we don't have that, then we don't really know if the CPUs are vulnerable to side channel attacks. So I think this is one of the problems that we have here. Okay, and that concluded my talk, so thanks a lot for your attention. If you have any questions, then I will be happy to answer them.